lecture 25 of our series on numerical methods in civil engineering, we will wind up our discussion of analytical methods for partial differential equations by discussing analytical techniques for solving elliptic partial differential equations. Function phi x, before doing so I want to talk a little bit about a very important result which is known as the mean value theorem, right, mean value theorem, and which starts with a function phi of x which satisfies Laplace's equation, and if any function phi of x which satisfies Laplace's equation is said to be a harmonic function, and all harmonic functions satisfy what is called the mean value theorem, right. All harmonic functions satisfy the mean value theorem. So, what does the mean value theorem say? It says that the value of a function at any point x0 is equal to the integral, first you take the integral of that function value phi over any sphere with radius, any radius centered at x0, and you divide it by the area of the sphere. So, basically to find what, it is very important, because what it says that if you want to find the function value at any point, right, what you need to do is to take the value of the function on any sphere, any arbitrary sphere surrounding that point. You take the value of that function on that sphere, right, and you take the integral of that value over that sphere, right, and then you take the average. So, you integrate it and divide it by the area of the sphere, and whatever value you get is going to be the value of the function at the center of the sphere, right. So, at any point x0 is equal to the mean value of phi over any sphere with center x0 in the domain of harmonicity. Domain of harmonicity meaning that we have to make sure that in that sphere Laplacian of phi is equal to 0 everywhere, right, because we are interested in finding phi such that it satisfies Laplace's equation, right. So, this can readily, we want to show this, and we are going to show this in spherical coordinates. Since we are looking at a sphere, we are integrating over a sphere, we need to use spherical coordinates, and spherical coordinates, for just to remind you, consists of a coordinate system like this. If this is my Cartesian coordinate system x, y and z, my any point I can describe the location of any point in the Cartesian system as x, y, z, in the spherical system as r, theta and psi, where r is the distance, radial, the distance of that point from the origin, theta is the angle that radial vector makes with the z axis, and psi is the angle which the projection of the radial vector on the xy plane makes with the x axis, right. So, in this system theta goes from 0 to pi, psi can go from 0 to 2 pi, theta can go from, as you can see, r can go from here to here, right. So, theta can go from 0 to pi, while psi can be anywhere between 0 and 2 pi. So, we are going to consider spherical coordinates, and we are going to consider phi at a point x on a sphere of radius r centered at x0. So, phi at x0 plus r is equal to, in spherical coordinates, phi evaluated at x0 plus r in terms of spherical coordinates is phi evaluated at x0 plus r cos theta by y0 plus r sin theta sin psi z0 plus r sin theta cos psi, where x0, y0 and z0 is the origin of my spherical coordinate system, right. So, x0, y0, z0, this is my point x0, y0, z0, say, right. So, where r is equal to x minus x0, and theta and psi are the polar angles of r with x0 as the origin as shown in the figure. So, what does the mean value theorem say? It says that the average value, we have to calculate the average value over that area of that sphere, right. So, how do we do that? Well, we take phi bar, which is the average value at r x0, r meaning the radius of the sphere, right. I am evaluating it at a point on the surface of the sphere. So, phi is a function of r, the vector r, it is not the spherical coordinate r, right, it is the vector r and the center of the sphere of the system x0, and that is equal to 1 by 4 pi r square, which is the total area of the sphere, right. Here r is now the radius of the sphere, and then I evaluate that function, and this is my infinitesimal area on the surface of the sphere, r square sin theta d psi d theta. And if I carry out, so this r square cancels out, and I get something like this, right. Then I take the derivative of phi bar with the radial distance. If I do that, I get del phi bar del r, which gives me del phi del r. Again, I can take it inside the integral because the integral does not depend on r, right. So I take that partial derivative with respect to r inside the integral. I get del phi del r sin theta d psi d theta, which I can write as, again I multiply the numerator and the denominator by r square. So I get 1 by 4 r square del phi del r r square sin theta d psi d theta, right. And this is again my infinitesimal area ds, right. So I get 1 by 4 pi r square del phi del r ds, where ds is an elemental area on the sphere surface, right. So we have got that far, right. But before going any further, let me go take a little sidetrack and try to talk about the gradient operator on the surface of the sphere, right. So, on the surface of the sphere, we know r is equal to x minus x 0 square plus this, right. So, x is a point on the surface of the sphere, x 0 y 0 z 0 is the origin. So, r can be written like that, right. So, I can write partial with respect to x is equal to partial with respect to r and partial of r with respect to x. So, that gives partial of r with respect to partial with respect to x gives me x minus x 0 by r. From this expression from r, if I take partial of r with respect to x, I get x minus x 0 by r, and I have partial with respect to r. Similarly, I get del del y is equal to y minus y 0 by r del del r, del del z is equal to z minus z 0 by r del del r. Now, what is this x minus x 0 by r? It turns out this x minus x 0 by r is the component of the normal at the point x. So, if I consider the point x on the surface of the sphere and I consider the normal to the sphere at the point x, the components of that normal in the x, y and z directions are given by x minus x 0 by r, y minus y 0 by r, z minus z 0 by r. Well, how is that? Let us take a quick look. So, suppose my normal is nx ex, ny ey, nz ez, right, and I am evaluating the normal at a point x on the surface of the sphere. So, what is the nx component of that normal? It is x minus x 0 by r, right. So, the vector is x minus x 0 ex, y minus y 0 ey, z minus z 0 ez. So, the normal is just the x component of the normal is just x minus x 0 divided by the norm of that vector r, right. So, nx is x minus x 0 by r, ny is a y minus y 0 by r, and z is equal to z minus z 0 by r, z 0 by r, right. So, n dotted with gradient of phi, suppose I have a function phi defined on the surface and I am evaluating its gradient. The gradient by definition, grad phi by definition is del phi del x ex plus del phi del y ey plus del phi del z ez. So, n dotted with grad phi is equal to nx del phi del x plus ny del phi del y plus nz del phi del z. But now, what about this? This is del phi del x, right. We have seen that we can write del del x as x minus x 0 by r del del r, right. So, what is this? This we already know is nx, right. We saw that this is nx, right. So, del del x is nx del del r, right. So, we have nx del phi del x is equal to nx del phi del r plus ny del phi del y is ny del phi del r plus nz del phi del z is equal to nz del phi del r, right. So, we take out del phi del r outside and we have nx plus ny plus nz which gives me 1, and I get del phi del r. So, what this shows is that if I evaluate the gradient on the surface of the sphere and take the dot product of the gradient with the normal to the surface of the sphere, that gives me how phi is varying with the radial distance, right. It gives me del phi del r, right. Therefore, we can write our equation, which was, I don't know where that is, I suspect it is this, right. I am talking about this, right. So, del phi bar del r, I can write this as del phi bar del r is equal to 1 by 4 pi r square. Go back, let us go back again. So, del phi bar del r equal to 1 by 4 pi r square del phi del r, and that is nothing but n dotted with grad phi, right. So, that is equal to n dotted with grad phi ds, right. But recall, in our previous lecture we showed that if a function satisfies, if the function phi satisfies Laplace's equation, right, then by its very nature, right, the integral of n dotted with grad phi over the surface must be equal to 0. We showed that last time, right. So, what does this mean? This means that del phi bar del r must always be equal to 0, right. And what does that mean? That means phi bar is a constant and its value does not change with the sphere radius, right. So, I am taking a radius, I want to evaluate the function at a certain point. So, I am evaluating the function on the surface of the sphere and I am dividing it by the area of the sphere. So, what I have shown here is that irrespective of the size of the sphere, this I mean whatever be the sphere may be of infinite size, sphere may be of finite size, does not matter, right. Phi bar is always going to be the same, right. So, from the definition of phi bar, it can be shown using something known as the localization theorem. Basically, it is intuitive, but if we want to show it rigorously, we have to use something called the localization theorem. But since it is intuitive, I did not go into that. But what it basically says is that in the limit as r goes to 0, phi bar must be equal to phi of x 0, right. Why is that? Well, the size of this, whatever be the size of the sphere, my phi bar is not changing, right. So, I make my sphere smaller and smaller, and the limit that r goes to 0, phi bar, it has to be equal to the value of the function at x 0, right. So, therefore, phi bar is equal to phi of x 0 irrespective of r, which proves the mean value theorem, right. So, that is important. In many why is it important? Well, because in many applications we are required to solve Laplace's equation in a spherical domain, particularly in fluid mechanics, in acoustics, in many applications, right, even in heat transfer, right. Suppose people are interested in solving in acoustic problems, they are interested in problems of scatter, right, of scattering problems, right. So, they have or for instance problems of bubble formation, when you have a bubble forming in a infinite fluid and the bubble is rising up from somewhere in the bottom of a body of water and it rises up, right. So, how is that, what is the mechanics behind that, when is the bubble going to burst, things like that, right. So, so in all those situations it is necessary to describe the physics using spherical coordinates, right, and we need to solve Laplace's equation. Well, why do we need to solve Laplace's equation? Well, again, because we are considering, in most cases we are considering irrotational inviscid flow, right. So, potential flow, right, that is why we need to solve Laplace's equation. Okay. So, now that we have introduced the spherical coordinate system, we want to solve such a problem, right, and introduce in the process another powerful tool to solve partial differential equations, the method of Green's functions, right. So, up till now we have looked at two methods. We have looked at the method of eigenfunctions, we have looked at the method of using transforms, right, using Laplace's transform, right. Now, we want to talk about the method of Green's functions, right. So, the Laplacian coordinate operator in spherical coordinates is expressed in terms of variables r, theta and psi as this, right, 1 by r square del r this. So, in terms of partials with respect to psi and partials with respect to theta, right. Now, consider a function phi hat which I define to be equal to minus 1 by 4 pi r, right. So, r being the radial distance of that point from the origin, right. So, I am defining a function phi hat which is at any point I am going to define that function, and the value of that function is going to be 1 by 4 pi times the radial distance of that point from the origin, right. So, and it is clear that if r is not equal to 0, Laplacian of phi hat is always going to be 0. So, phi hat by definition is always going to satisfy Laplace's equation unless r is equal to 0. You can see that these are partials with respect to psi and theta. There is no dependence of phi hat on psi and theta. So, the only part that can contribute is this del r of minus 1 by 4 pi r is going to give me 1 by r square term, right. R square cancels out, I have a constant, I have del r of that is going to give me 0, right. So, by construction this function is going to always satisfy Laplace's equation unless we are at the origin, and this solution of Laplace's equation in spherical coordinates is known as the fundamental solution. Next, we consider a function f of x where f of x is a smooth but otherwise arbitrary function, that is derivatives are continuous, but its value is totally arbitrary and is defined in a domain omega centered about the origin such that mod of x less than epsilon for all x belonging to omega. So, it is centered around the origin, but it has a size which is bounded by epsilon, right, its radius bounded by epsilon. So, let us take the integral of f of x with Laplacian of phi hat, right. So, we know that Laplacian of phi hat is always equal to 0 except at the origin, right. So, let us rewrite this f of x as f of x minus f of 0 Laplacian of phi hat plus f of 0 Laplacian of phi hat, just I have added and subtracted f of 0, right. Then we look at this part of this equation, right, and if we look at this part and then we use divergence theorem, right, I know that the Laplacian is nothing but the divergence of the gradient, right. So, f of 0 is integral of omega divergence of gradient of phi hat, right. So, this can be written as divergence of gradient of minus 1 by 4 pi r, because that is the form of phi hat, right. We just said that phi hat has the form minus 1 by 4 pi r, and that is equal to f 0 n dotted. So, then I use the divergence theorem. I bring this is divergence of this vector which is gradient of this scalar, right. So, if I use the divergence theorem, I can write it as n dotted with gradient of minus 1 by 4 pi r ds. Now, recall that we showed just a little while earlier that n dotted with the gradient of any function is nothing but del r of that function on the surface of the sphere, right. We just showed that n dotted with the gradient is the rate of change of that function with respect to r, right. So, we can write f 0 divergence of gradient of minus 1 by 4 pi r d omega as f 0 integral of over del omega, that is on the boundary, and now we are replacing n dotted with grad of this by del r, right, del r of minus 1 by 4 pi r. So, that is going to give me 1 by 4 pi r square, right, and then again I replace ds by r square sine theta d psi, the incremental infinitesimal area I replace in terms of r theta and psi, right. R square cancels out, right. I pull out my 4 pi r outside, and then I have this integral, and if you integrate this exactly comes out to be equal to 4 pi, right. So, that 4 pi cancels out and I am left with f of 0, right. So, this term is actually f of 0, right. This actually contributes just 1, right. So, this term is f of 0, and we can show that as omega tends to 0, in the limiting value this function, since this function is smooth, since this function is smooth, as omega tends to 0, this function goes to 0. You can see why that is happening, right? Because as omega becomes smaller and smaller, f x becomes closer and closer to f of 0, right? And it goes, and since it is smooth, it does so in a continuous fashion, right? So, as omega goes to 0, this integral also goes to 0, right? So, we can write in the limit that omega tends to 0, this integral actually goes to f0, right. So, this integral goes to f0. So, in the limit omega goes to 0, integral of f of x Laplacian of phi hat d omega is equal to f0. Now, let us take a step back and recall that there is something called the Dirac Delta function, right, and the Dirac Delta function has the property that it is 0 everywhere in my domain except at x is equal to 0, and moreover if I integrate del x the Dirac Delta function over my domain, I am always going to get 1, right. So, this is different from the Kronecker delta, right, which is but this is the Dirac delta function. So, in this case delta x is equal to 0 everywhere except at x is equal to 0, but the integral of delta x over my domain is always equal to 1. Hence, if I have a function f of x and I have delta x, if I take the product and I integrate it over my domain, this is going to give me, this product is going to be 0 everywhere except at the origin, right. Except at the origin, its value is going to be undefined. The value of delta x is undefined. The only thing that I know is that if I integrate delta x over the domain, I am going to get 1. So, this is, but since delta x is 0 everywhere, the value of x does at any other point other than 0 is not going to count, right, because this is going to give me 0. But over that but at x is equal to 0, it has the value f0, and then it is going to scale the value of the Dirac delta function, and what we are going to get is something like f0, right. So, if I compare these two equations, if I compare this equation and compare this equation, we see that Laplacian of phi hat by construction, since Laplacian of phi hat is equal to 0 everywhere by construction, right, except at the origin, right, it is very similar to the Dirac delta function. In fact, it is exactly equal to the Dirac delta function because it acts in exactly the same way, right. I know that Laplacian of phi hat is equal to 0 everywhere, right, in the everywhere in my domain except at the origin, and the origin it is undefined because as you can see there is an r at the bottom. So, r as r goes to 0, that becomes undefined, right. So, it is very similar to the Dirac delta function. Now, I see that if I take any arbitrary function and scale it with Laplacian of phi and I integrate it over omega, then I get the value of the function at 0 at the origin, which is exactly what the Dirac delta function does, right. So, at the origin it behaves exactly like the Dirac delta function, outside far away from the origin it behaves exactly like the Dirac delta function. So, it has got to be equal to the Dirac delta function, right. So, Laplacian of phi hat must be equal to delta x, right. Laplacian of phi hat must be equal to delta x, where delta x is the Dirac delta function. In case my domain is not centered at the origin, but about an arbitrary point x, then we can write Laplacian, it should be y, I am sorry, but about some arbitrary point y, then we can write Laplacian of phi hat x minus y is equal to del x minus y, right. Why can we write that? Well, we can write that because the Laplacian operator is translationally invariant in space. What does that mean? Well, if I write my Laplacian like this, and then the origin at 0, right, I have something like this. So, del 2 phi del x1 square plus del 2 phi del x2 square plus del 2 phi del x3 square, and then I shift the origin, right. So, I change my origin from 0 to x10, x20, x30, and such that we get a transformed coordinates like x1 prime, x2 prime, x3 prime, where x1 prime is equal to x1 minus x0, x2 prime equal to x2 minus x0, x3 prime equal to x3 minus x0, then Laplacian with respect to x prime is going to be exactly equal to 0, right, can be shown. So, it is translationally invariant in space. So, I can write Laplacian of phi hat x minus y is going to be exactly equal to delta of x minus y. Translationally invariant means the properties remain exactly the same, right. It is just that the origin has shifted. So, let us go back to the equation. Laplacian of phi hat x minus y is equal to delta x minus y, and we know that phi hat was of the form 1 by 4 pi r when the origin was at 0, right. So, if my origin has shifted to y bar, my phi hat is going to be slightly different. It is going to be 1 by 4 pi mod of x minus y, right. Instead of r, I have mod of x minus y, and that is going to be given by this, right, 4 pi root of x1 minus y1 square plus x2 minus y2 square plus x3 minus y3 square. So, we look at this function and let us multiply both sides of that equation. Laplacian of x square phi hat x minus y is equal to del x minus y by rho y, right, which assuming that x is my independent variable is a constant. So, let us for the time being, rho of y is nothing but the value of rho of x evaluated at y, right. So, x is still my only independent variable, and rho of y, let me think of rho of y as a constant. It is the value of rho of x evaluated at y, and in that case I get Laplace. So, since it is a constant, I can pull it inside my Laplacian operator, right. I can pull it inside my Laplacian operator, and I get Laplacian square rho of y phi hat x minus y is equal to rho y del x minus y. Next, I assume that instead of assuming that the position of the origin is fixed at y, I make y variable, right. So, my origin now becomes variable. Instead of thinking of y as a point in space, as a fixed point in space, now I assume that y is a variable. So, my origin can be anywhere in this space, right. Then this equation involves two independent variables. It not only involves the independent variable x, right, and its components, right, as it also involves the independent variable y, right. Then if we integrate this equation, so now there are two independent variables x and y, and I am going to integrate this equation with respect to y, right. I am going to integrate that equation with respect to y throughout my volume V, right. So, I take the integral of Laplacian of rho y phi hat x minus y dy, right, over the volume V. So, this I know is 1 by 4 pi x minus y, right. So, I have Laplacian of x square minus 1 by 4 pi integral of V rho y mod of x minus y dy, and if I denote this integral 1 by 4 pi integral rho y by mod of x minus y dy as another variable phi bar, right, another variable phi bar, where phi bar is now a function of x only, right, phi bar is a function of x only, right. In that case I have, because I am integrating it out with respect to y, right. So, it is now a function of x only, right. So, phi bar, so this is equal to Laplacian of square phi bar, right, because I am denoting this as phi bar, and this integral is known as Poisson's integral, But let us recall Laplacian of x square rho of y phi hat x minus y dy is equal to rho of y del x minus y, because I know that Laplacian of x square phi hat x minus y is just like del x minus y. We have seen that before, right, exactly here, right. So, that is del x minus y. So, then I have rho y del x minus y, I am integrating over dy. So, again I am going to get rho of x, right, it is going to give me rho of x. So, what do we have? We have this thing is equal to rho of x and this thing is equal to Laplacian of phi bar, right. So, I have Laplacian of phi bar, where the Laplacian is now with respect to x, x is my independent variable, right. Laplacian of phi bar is equal to rho of x and phi, if so this gives me a non-homogeneous form of the elliptical equation, right. So, Laplace's equation has Laplacian of x equal to Laplacian of that function equal to 0. This is Laplacian of phi bar is equal to rho of x, and this equation is known as Poisson's equation, right. This is Poisson's equation, and you can see that for the Poisson's equation I already have a solution, right. If Laplacian of phi bar is equal to rho of x, then to find phi bar all I need to do is to evaluate this integral, right. What is that integral? I take rho of y divided by mod of x minus y. Suppose I want to find phi bar at some point x, right. I want to find phi bar at some point x in my domain, right, and I know that phi bar satisfies Poisson's equation. So, all I need to do is to evaluate this integral rho of y divided by mod of x minus y, where x is the point where I want to find my where I want to solve Poisson's equation, evaluate that integral, and that is my solution, right, and that is actually a particular solution to this equation, right. It is a particular solution to that equation, right. And this is up till now we have not talked anything about boundary conditions, right. So, this equation, this Poisson's equation may have certain boundary conditions as well, right. So, we have this solution does not include the effect of all those boundary conditions, right. So, it is a particular solution. So, there is going to be another part which includes the effect of the boundary conditions. So, to obtain the complete solution we have to specify the boundary conditions on phi bar at the boundary of the domain, right. So, in order to let us suppose phi bar is equal to g on my domain which is del v. So, I am missing a v here. So, it is phi bar is equal to g on del v, then the complete solution phi bar is given by the superposition of the solution which satisfies the homogeneous equation Laplacian of phi bar equal to 0 and the particular solution. The homogeneous solution, the solution to the homogeneous equation must satisfy the boundary conditions. Actually, both of them together must satisfy the boundary conditions, right. So, what is phi bar? Phi bar is equal to phi 1 bar plus integral of rho y phi hat x minus y dy. This is my particular solution. This is the solution to the homogeneous equation, right. Therefore, on the boundary phi 1 bar must be equal to f minus this value, right, because this value, this is what I get, right. So, for phi bar to be equal to g on del omega. So, this must be g, I apologize again. So, phi bar to be equal to g on del v, then phi 1 bar must be equal to f minus this on the boundary, right, g minus that on the boundary. So, we have found a way to solve Poisson's equation. We have found a way to solve Poisson's equation if using the fundamental solution to the Laplace's equation. So, we have firstly looked at Laplace's equation, right, and we found the fundamental solution of Laplace's equation which is phi hat, right, and then we looked at Poisson's equation, right, where the which is basically the elliptical operator equal to a non-zero value, right, and we said that if we know the fundamental solution to Laplace's equation, we can also construct a solution for Poisson's equation using that fundamental operator phi hat and the value on the right hand side of Poisson's equation which is rho, right. let's go back and take a look at Poisson. That was my Poisson's equation, right. So, the solution of the Poisson's equation I have been able to construct in terms of the fundamental solution of Laplace's equation and my operator, right. Plus there is this term which is the homogeneous solution, which is nothing but the solution of Laplace's equation subject to those boundary conditions, subject to those boundary conditions. Okay. So, that is one approach, to solving Laplace's equation using the fundamental solution, right, in spherical coordinates, right. We want to talk about another approach which is a very powerful approach, because it can be because it allows us to solve Laplace's equation for very general boundary conditions. So, whatever be my domain, right, whatever be my boundary conditions, I can solve Laplace's equation using this Green's function approach, right. So, the Green's functions are constructed to satisfy Laplace's equation as well as boundary conditions homogeneously. That is, irrespective of the actual boundary conditions, the Green's function is always 0 at the boundary. Look, this is very analogous to your eigenfunction approach. Remember that what does the eigenfunction do? What do we do in the eigenfunction approach? We try to find a solution of my operator, of my linear operator, which satisfies the homogeneous boundary conditions, right. So, the eigenvalue problem, right, always has homogeneous boundary conditions, and using those eigenfunctions, solution to that problem which are the eigenfunctions, right, I can construct any solution to my partial differential equation, right. So, they form a basis for my solution space, right. Similarly, Green's functions also, right. Green's functions, you can think of them again as solutions to Laplace's equations, satisfy the boundary conditions homogeneously, but once we know the Green's function, we can construct the solution for any arbitrary boundary condition. So, Green's functions satisfy Laplace's boundary condition for Laplace's equation for homogeneous boundary conditions, right. It satisfies Laplace's equation for homogeneous boundary conditions, but using the Green's function I can solve the non-homogeneous problem, right, and we will see how we can do that. But in order to construct Green's functions, we make use of something known as Green's identities, which are basically rather simple. Basically, we consider two smooth functions phi and psi defined over a volume V with boundary del V. Then we write Green's first identity in the following manner, which is just really straightforward, because it is just writing the Laplacian operator in terms of its definition, in terms of the divergence and the gradient, right. So, psi, if I take the integral of psi times Laplacian of phi, I can write it as divergence of psi times the gradient of phi minus gradient of psi dotted with gradient of phi. This is a very simple identity from vector calculus. It can be proved almost trivially, right, using lots of ways of proving it. But psi Laplacian of phi is equal to divergence of psi gradient of phi minus gradient of psi dotted with gradient of phi, right. And then we say we use the divergence theorem on this part, right. So, divergence of psi grad phi is nothing but psi grad phi dotted with n over my surface, right, over my surface, minus this part remains the same, the gradient of psi dotted with gradient of phi, right. And this gradient psi grad phi dotted with n is nothing but del phi del n. We have seen that before, right. That is nothing but del phi del n, right, psi del phi del n dsy. So, again I have made a mistake here, this should be dsy, because this is the integral over the surface, right. So, psi del phi del n dsy minus gradient of psi dotted with gradient of phi dy, right. So, that is my first identity, Green's first identity. To get Green's second identity, we interchange phi and psi, right. So, now we have interchange phi and psi, we have phi Laplacian of psi dy is equal to phi del psi del n minus grad phi grad psi dy. So, all we have done is we have interchanged the phi and psi in that expression, right, and then we subtract this from this. If we subtract this from this, this part you can see vanishes because this is identical to that. So, that part vanishes and we have psi Laplacian of phi minus phi Laplacian of psi integrated over the volume must be equal to psi del phi del n minus phi del psi del n integrated over the area. So, that is my Green's second identity, right. And to finally to get Green's third identity, we make a further assumption. Up till now, the only thing we have assumed over phi and psi about phi and psi is that they are smooth functions. They are defined over the volume V with boundary del V, right. We have not assumed anything else. So, now we make the additional assumption that Laplacian of phi is equal to 0, right. If we assume that Laplacian of phi is equal to 0 and we assume that psi is my fundamental solution to Laplace's equation, that is psi is equal to phi hat, which is equal to minus 1 by 4 pi r, and then I substitute these values, these conditions in Green's second identity. If I do that, what do I get? Well, I have psi Laplacian of phi. I have assumed that Laplacian of phi is equal to 0. So, this first term is going to give me 0, and then I have minus phi Laplacian of psi, right, dy. So, that gives me minus phi Laplacian of 1 by 4 pi r dy, right, and that is equal to the integral over the surface, right. That is equal to the integral over the surface, which is psi del phi del m, psi being equal to 1 by 4 pi r. So, I have 1 by 4 pi r del phi del n minus phi del psi del n, right. So, that is equal to minus phi del n of 1 by 4 pi r dsy, right. So, substituting these in Green's second identity, I get that. But let us recall Laplacian of 1 by minus 1 by 4 pi r, Laplacian of my fundamental solution is nothing but my Dirac delta function, right, is nothing but my Dirac delta function. So, I have delta x minus y phi y, and that is going to give me phi of x, right. So, what do I have? I have on the left hand side I have phi of x, and that is equal to 1 by 4 pi 1 by r del phi del n minus phi y del n 1 by mod of x minus y, where I have replaced r by mod of x minus y here, right, and I have pulled out my 4 pi outside the integral, right. So, this what do you see? Well, you see that using Green's third identity, right, if I want to find, if I know that phi satisfies Laplace's equation, I already have my solution phi in terms of using Green's third identity, provided I know the value of the gradient and the value of the function on the boundary, right. So, you can see it is automatic, right. So, I want to I have only thing I have assumed is that Laplacian of phi equal to 0, that is phi is a solution of Laplace's equation. Well, what is the solution? Well, I can always find the solution if I know the value of the solution at the boundary and the gradient at the boundary. Green's third identity allows me to find the value, find the function at any point in the domain if I know the value of the function at the boundary and the value of the derivative, the normal derivative of the function, right. You can see the power of this approach, right. So, it can find the value of the function at any point, right. I want to find a function which satisfies Laplace's equation, right, and somebody has told me that the value of, I know the value of the function at the boundary and the gradient at the boundary, right. If I know that, I can solve, I know the function straight away, right. So, given the boundary conditions, I know the function, right. That is why Green's functions are so powerful, right. So, Green's third identity suggests that if we know phi as well as its normal derivatives at the boundary, it is possible to determine phi throughout the domain using this result, right. It is possible to know the function anywhere in the domain, right. However, in practice we do not know at any point on the boundary, we usually do not know both the function as well as its derivative, right. If both the things are known, the problem is not usually ill posed, right. If you go back to your mechanics, right, if you go back to your structural mechanics, at a boundary, right, we cannot specify both the displacement as well as the traction, right. You can specify either, right. If you specify both, then the problem is ill posed, right. So, usually we do not know the function value as well as its derivative at a point. We either know the function value or we know its derivative, right. So, an important point is the following. Since before coming back again, I have taken a little sidetrack, but it's worth emphasizing here. Since Laplace's equation is a linear equation and the coefficients are constant, if a phi hat is a solution, that is Laplacian of phi hat is equal to 0, then Laplacian of gradient of phi hat is always going to be 0. Why is that going to be true? Well, think of it like this: Laplacian of phi hat. What does that mean? Del x1 square phi hat plus del 2 del x2 square phi hat plus del 2 del x3 square phi hat, right. And then suppose I want to take the gradient, right. So, if I take gradient, I take a part again del x, right, del y, del z, or del x1, del x2, del x3. So, since those coefficients are constant, I can pull in my gradient operator inside my Laplacian, right. So, the order of the differentiation does not make a difference because my coefficients are constant, they do not depend, or there is no x dependence of the coefficients of Laplace's equation, right. So, since that is true, what that tells me is that Laplacian of grad of phi hat had better be 0 too, right. If Laplacian of phi hat is equal to 0 and I take gradient of both sides, I can pull the gradient in because of the nature of this operator. So, if phi hat satisfies Laplace's equation, gradient of phi hat must also satisfy Laplace's equation, and if gradient of phi hat satisfies Laplacian of Laplace's equation, the second gradient, if I operate on that with another gradient operator, that's got to satisfy Laplace's equation as well. So, if I have grad to the power n of phi hat, all of them are going to be solutions of Laplace's equation. We can see that this gives rise to something very important known as spherical harmonics, right. We are going to talk briefly about them if we get time, but this property is very, very important. So, we saw Green's third identity, right, and we saw that using Green's third identity, I can always find a solution of Laplace's equation provided I know the function as well as its derivative on the boundary, right. But then we said that, well, it is not usually possible to know both the function as well as its derivative on the boundary. So, what do? Well, we do this. In Green's second identity, we write psi is equal to g is equal to 1 by 4 pi r plus u, right. We define psi to be 1 by 4 pi r by u, r is mod of 1 by r is equal to mod of x minus y. So, that is my fundamental solution, right. So, here before that, what did we do? We assumed that psi is nothing but my fundamental solution, right. In Green's third identity, in Green's second identity, we assume that psi is my fundamental solution. Now, I am saying that, well, do not assume psi is my fundamental solution, you assume psi is equal to my fundamental solution plus some another term, right. You assume that psi is my fundamental solution 1 by 4 pi r plus another term, right. So, we are changing track slightly, right. So, first we assume psi is equal to 1 by 4 pi r. We obtained a solution for phi, but we said that that solution it is not very useful, because it tells me that I must need not only my function value, I must need my derivative also at every point in the boundary, right. So, that is not very useful. So, now I say that well then let instead of assuming psi equal to 1 by 4 pi r, let us assume psi is equal to 1 by 4 pi r plus u, right, where u is harmonic in y, where u satisfies the solution of Laplace's equation in that domain, right. And then I substitute that again back in my Green's second identity. So, which was this, right. I substitute that back again in Green's second identity, and if I do that, I get now g of Laplacian of phi, because Laplacian, you can go back and take a look, let us go back and take a look. So, we have psi Laplacian of phi minus phi Laplacian of psi, right. So, g Laplacian of phi minus phi Laplacian of 1 by 4 pi r, right. If you do that, it comes out to be that, and then on the right hand side we have g del phi del n minus phi del g del n. G del phi del n minus phi del g del n, right. Psi is equal to g, right. So, g del phi del n minus phi del g del n, right. So, psi Laplacian of phi minus phi Laplacian of 1 by 4 pi r, because Laplacian of u is always 0, right. So, g psi Laplacian of phi minus phi Laplacian of psi, Laplacian of u is going to give me 0, I have Laplacian of 1 by 4 pi r, right. And then we recall that Laplacian of 1 minus 1 by 4 pi r is equal to my Dirac delta function with argument x minus y, right. Then what do we get? We get g Laplacian of phi minus phi del x minus y integrated over dy. So, that is going to give me phi of x, right. That must be equal to integral with over the volume over the surface of g del phi del n minus phi del g del n, right. So, now this gives me phi of x is equal to g del phi del n minus phi del g del n minus g Laplacian of phi, right. I have brought this Laplacian of phi to the right hand side, right. So, I have brought this to the right hand side, I have phi of x here and I have this thing, right. Now, if I want to find out phi that satisfies Laplace's equation, if I want to find out phi that satisfies Laplace's equation, then this term is automatically 0, right, because phi satisfies Laplace's equation. So, this term is automatically 0, and in that case phi is going to be given by g del phi del n minus phi del g del n s y, right, phi del g del n s y. If we can find Green's function g such that g is equal to 0 on my boundary, then I have a solution. So, if I find g such that g is 0 on the boundary, then I am getting phi of x is equal to minus phi del d del n dsy. So, you can see now I do not need the function value as well as its derivative, I only need the value of the function phi on the boundary, right. So, if I know if g is going to be 0 everywhere on the boundary, right, then I can find out phi at any point in my domain only if I know the value of phi on the boundary. I do not need to know both phi and its derivative at the boundary, which makes the problem well posed, right, which makes the problem well posed. So, if g is equal to 0 on del v, then I can find phi x is equal to minus phi del g del n dsy. So, if I know phi on my boundary, I know g, right, then I can find out phi x, right. So, the idea is this: if I know my Green's function, and the Green's function satisfies the boundary conditions homogeneously, right, which was another very important criteria, right, for Green's function, right, then I can find my solution to Laplace's equation if I know my value of that function on the boundary, if I know my phi on the boundary. So, the only requirement is that phi must be prescribed on the boundary. So, phi must have Dirichlet type boundary conditions. Similarly, on the other hand, if we can find g such that the gradient of g is equal to 0 on the boundary, right, then what happens? Then this term is going to be 0, right, this term is going to be 0, and in that case I can always find phi if I know my gradient of phi on the boundary, right. So, they are complementary. If I know if g is equal to 0 on the boundary, then I must know phi on the boundary. If del g del n is equal to 0 on the boundary, then I must know del phi del n on the boundary. So, if I know that, I can find out my phi of x, right. So, this is basically the fundamentals of the Green's function approach, right, for solving both the Dirichlet as well as the Neumann's boundary condition. So, I thought I would finish elliptic equations this time, but I am still left with the series solutions. I am not sure if we have time to cover that. So, we have to take a decision on that, whether we want to continue with series solutions or move on to numerical techniques for partial differential equations. Thank you.